Hey everyone, and welcome back to C++ Under the Microscope. Today we are tackling a viewer suggestion that came in as a comment. What really happens under the hood with self-calling lambdas using this in C++23? We will look at the new syntax, compare it with old techniques like std function and the Y-combinator, and then dive deep into the assembly. Let's check the new syntax. Here is the new syntax. Let's check this Microsoft blog post where they talk about this new feature. As they say, usually when we call an object's member function, the object is implicitly passed to the member function, despite not being present in the parameters list. This example here, we don't really pass this parameter, but it's being passed anyway. And with this new syntax, we can do this explicitly as shown here. A quick refresher, a lambda is just a syntactic sugar for a compile-generated functor. Let's see the example. And let's check it with CPP insights. This will remove the syntactic sugar. This lambda was translated into a class with this operator overloaded. And here we can see we create an instance of that lambda here. And we just call the operator. And we pass it the number 3. And it will come here and execute this line. So that's the lambda. If we capture values here, they will become data members of the class. Let's actually see an example. Here it is. Again, it generated a class lambda, and here is the reference to the test variable here. We have constructor, and when the lambda is created, we can see that the test variable, this one here, is passed to the constructor here, which then sets it here as well. Now, recursion inside the lambda used to be a pain. Let's look at how we did it before C++23. This works, but std function uses type erasure. It hides the real callable behind the virtual call or a function pointer. That means every recursive call goes through an indirection, which can be costly in performance-sensitive code. Plus, you need to capture factorial by reference, which can be tricky if the lambda outlives the scope. Here is the code without the syntactic sugar. We have the function here. We call this factorial. And this is the lambda. This lambda here. Let's check it. First, the constructor. We have to pass it this std function. And here we store the factorial, which is this thing here. And to it, you assign the lambda itself. So this thing holds in itself the lambda. That's what enables to call this factorial.operator overload. The other way to write that is with Y-combinator. It's a functional programming trick that lets you create recursive lambdas without needing a name. It's elegant, but it's also complex and unfamiliar to many developers. And while it avoids the std function's overhead, it still passes the functor object around. And just for fun, let's check the CPP insights for this. As you can see from the code, we create Y and we pass it a lambda. In fact, this initializes this F here, and then we call the lambda, passing this pointer and forwarding the parameters, the args. It's elegant. I would give it that. Both methods work, but they have drawbacks, either runtime overhead or complexity. That's why C++23 introduced deducing this, a simple zero overhead way to write recursive lambdas. With deducing this, we add an explicit object parameter. Inside self refers to the lambda itself, so we can call it recursively. Let's check what the compiler will generate with CPP insights. Here is it. It creates a class. We have this overload here. And we see that it's a template. This is the type. We use it here. And if we use that thing, here is the generated template. And what we can see, we create an instance from that class that's called lambda for 18. This is the generated template of this overload, and we pass the lambda for 18 here as a parameter. And now self is this class here. And in the function body here, we see that we call self, we call it recursively. So we saw that self has the exact type of the lambda. And as we saw with CPP insights, that means that this is a direct call, no indirection, no type erasure. And because the lambda has no captures, the self parameter can even be optimized away entirely. We'll see that in assembly. With O0, we can see that it has a recursion function call. So here it calls the self, which is brings us here again. With O1, that thing is optimized away, and it's reduced to this jump instruction here. With O2, it's so optimized away. Yes, there is no lambda here or function call. So how does deducing this stack up against the old ways? With SDF function, it's simple to write, but every recursive call goes through type erasure, and that's overhead. With the Y-combinator, zero runtime overhead, but complex and unfamiliar. Deducing this has a simple syntax, zero overhead, it uses direct calls, and works seamlessly with captures. The key insight, the explicit object parameter, gives the compiler the exact type information, enabling it to devirtualize the call and even eliminate the parameter when it's not needed. A huge thank you to the viewer who suggested this topic. If you have a C++ feature you would like me to put under the microscope, drop a comment below. Don't forget to like and subscribe. See you next time. Until then, keep exploring.